everyone. So today we are actually going to go over permutations, which is what we want you to learn from this week. And our first problem, problem 8, is how many ways can n people be seated in a row of n chairs? Alright, so before I go into the answer, I'll actually, start with an example. Instead of using n, I'm going to actually pull up a number. So let's say that we have 7 people and 7 chairs. And you guys know how to count the number of ways we can seat 7 people in 7 chairs. We have 7 chairs, 1, 2, 3, 4, 5, 6, 7. 1 to 7. And 7 is also n. Alright, this is n and this is n. And 7 is equal to n is equal to 7. So for our first chair, we have 7 options, then we have 6 options, then we have 5, 4, 3, 2, 1. And that here, right here, is the number of ways we can seat 7 people in 7 chairs. And that is also equal to 7 factorial, right? So 7 factorial is equal to 7 times 6 times 5, we up to 1. And you'll see that this pattern, occurs for, if we just have a variable n. Instead of 7, we can write that if we want to seat n people in n chairs, that's equal to n factorial. So n factorial is n times n minus 1 times n minus 2 all the way up to 1. So this actually that's our formula for this problem. And so our second problem is, in how many ways can a row of k seats be filled from a set of n people? So before, let's say that here, the number of chairs is equal to k, right? And the number of people is equal to n. We denote this with these two variables. So in the equation that we did before, we're saying that n is equal to k. But right now in problem 9, we're saying that n does not necessarily equal k. So I'll do another example, but instead of having 7 people in 7 chairs, I'm going to say that k is equal to 4 chairs. So if we want to do that, well, 1, 2, 3, 4, we want to stop right here. We don't need this part right here. We're going to stop right here. We're only going to do 7 times 6 times 5 times 4. And so how do we do that with just variables? With just n and k? Well, as it turns out, what we do is that we start with 7 factorial, as before. But the problem with 7 factorial is that, see, 5, 4, 3, 2, 1. We start with 7 factorial, but we don't want this part. So how do we get rid of this part? Well, we have to divide, right? So let's say that we want to divide by 3 times 2 times 1. And that's what we get, 7 times 6 times 5 times 4. So how would you put this in a formula? Well, what you want to do is that you know that this is where we're starting off with. This is k, 4 is k, and 7 is n. And we want to delete this part. So this part is equal to n minus k factorial. And so just take a moment to verify that this is true. This right here, this section that we want to divide by, is equal to n minus k factorial. So in our scenario, it's equal to 7 minus 4 factorial, which is equal to 3 times 2 times 1, which is exactly what we want to divide by. So we want to find, we want to seat n people in k chairs. That would be equal to, starting with n factorial, divided by n minus k factorial. And this is the formula for permutations. Although you really don't need to memorize this, just to understand the concept. You have 4 chairs, you just start with 7 times 6 times 5 times 4. And this, when you divide by this, is just a way that you can express this through factorials and variables. And, problem 10 is pretty tricky. So we're actually going to be using what we learned from about permutations, and we're going to apply it to this problem. Our problem is, in how many ways can 6 different keys be arranged on a keychain? And the important thing to know about keychains is that they're different from lines and they're different from circles. So I'll start with an example again. Let's say that we have 4 different shapes. So we have a circle. And, actually, let's start with 3 different shapes. We have a circle, we have a triangle, and we have a square. So how many different ways are there to arrange these three different shapes in a line? Well, there's this one that I just drew out here. We can also start with a triangle, and then a square, and then a circle. We can also start out with a circle, and then a triangle, and then a square, and then I'm just going to quickly, draw out. Well, okay, first of all, in a straight line, how many different ways are there to place these three different objects in a straight line? That's just 3 factorial, which is equal to 3 times 2 times 1, which is equal to 6. So I'm going to draw all 6 combinations, and then I'll explain how we would have to divide again if this was actually in a circle. So we have these two arrangements. I should have started with this one's equal. Sorry, this one's the same thing. Should have started with a square, square, circle, triangle, then circle, square. All right, I believe I have all the shapes. So this is all 6 combinations or 6 different ways we can order these 3 different shapes in a straight line. But I'm going to tell you right now that if we're going to put these 3 shapes in a circle, that we would have to divide this number by 3. And the reason why this is because in a circle, these are the same thing, and these are all the same thing. And I'll explain this because I'll actually draw them in a circle. So I'll start with this as an example. This one we have square first, right? And then following square is circle. And then following circle is triangle. So that's one of them. Our second one, well, we start off with a circle. And following the circle is a square. And following the square is a triangle. And then for our third one, first we start off with a triangle. And then following the triangle is a circle, and following the circle is a square. And I'm claiming that when we put this in a circle, these are all the same. And I'm just taking these and I'm just, putting them in a circle. I'm saying that these are the same because the square follows the circle, which follows the triangle, which follows the square. So the circle is always going to be left of the square if the square was looking inside. Or if you're looking at it this way, you would say that the circle is always going to be to the right of the square. And so you can see that it's the same for this one. So sorry, this one is drawn out in the wrong order. A circle, circle, triangle, square. Triangle, square. Right. So you start with a circle, and then the circle goes all the way to the square, and then the triangle, and then the triangle follows the square, and the square goes back to the circle, right? So if you look at it from the square's perspective, the circle will always be left of the square. Like if you look at it from the square's perspective and you're looking into the circle, looking into the circle, the shape circle is always going to be left of you, and the shape that is triangle is always going to be right of you. And so that's why that we say that these are all the same. Because if you were to rotate them in a circle, if you were to rotate them, these would all look exactly the same. So imagine that you rotate it until it looks like this, until picture 2 looks like picture 1. If you can do that, they are, essentially the same combination. And if you can do that for this one, if you can rotate picture 3 into picture 1, then we say that they are the same. So because of this, because we are claiming that these 3 combinations are the same, and these 3 combinations are the same, we have to divide by 3 to get the true number of ways we can order these up. What I'm also claiming here is that this 2 is not equal to this. These 2 are not equal in a circle. And that's because the square, like the circle, follows the square. In this case, if it was going, that way, the circle follows the triangle. So these are not the same. You can't no matter how you rotate it, they're not the same order. There's no way you can rotate this to get this. All right, so if this was all, we had 3 shapes in a circle, then there would only be 2 different combinations. But it gets even more tricky when we're talking about keychains, because in a keychain, you can also flip it over. So instead of just rotating it like in a circle, you can also reflect it against itself. So if we can reflect this, not just rotating, we can reflect this, it's possible for us to reflect this object so that it looks like this. And we would just, reflect this down the middle like this. We reflect it, it'll look the same as number 2. And so because we can also reflect it, then we're going to also divide by 2 if this was a keychain. And remember, this all depends on what kind of, how they're situated, I suppose. So 1, we have lines, which is basically what we talked about before with permutations. Then we have circles, and in circles, we can rotate. And because we can rotate it, we also have to divide by n. And then for third one, we also have keychains. So in a keychain, we also have to apply the rules for circles, but we also have to divide by 2 because we can reflect it. So, this is kind of a finicky thing to get your head around. Try to understand this, and I will explain to you how that applies to our problem, which is in how many ways can 6 different keys be arranged on a keychain. So if it was just 6 different keys in a line, we would have 6 factorial. But because it's in a keychain, we have to apply the rules for both circles and the special rule for keychains. So in a circle, we have to divide by 6 again, because that's how many ways we can rotate it, or that's how many combinations. Okay, well, you saw what I drew out before. In a line, those 6 different rotations would be the same thing, because in a circle you can rotate it. And then in a keychain you have to divide by 2 again, because you can also flip it over. And so that takes away another half of the combinations that were in a circle. So if you divide this, we have 6 times 5, 4, 3, 2, 1, divided by 6 times 2, which is equal to 20 times 3, which is equal to 60. So in a keychain, there are only 60 different ways we can arrange these 6, what are they called? Keys. In a keychain, there's only 60 ways we can arrange these keys. But if they were not in a keychain, if they weren't just in a circle, then we don't need to divide by 2. We would actually have 120 ways in a circle. And if it was not in a circle and it was just, in a straight line, if you're just arranging these three keys in a line, then we would have 120 times 6, which is 6 factorial. So I hope this makes sense. You don't have to remember these rules here, but try to understand the concept and why we count lines, circles, and keychains differently. Thank you guys for watching, and I will see you guys next week.